All right, everyone, welcome back to week 10. The tutorial today is mostly about integration. And remember, integration is just the opposite of differentiation. So in calculus, you sort of have two main operations where one of them is differentiation, one of them is integration, and they kind of are opposites. Okay, so this is a tutor-led tutorial, so we'll be working through some of the problems together. So let me know how it's going in the chat if you have any questions or comments or something's not clear. We're going to be working through chapter 8 today. So here's the PDF, and it's on page 201, okay? So I thought because it's Monday morning, we can start with some of these more basic problems and discuss them, and then we can get through to some of the H or the harder problems, all right? Okay, so I'm going to start with 4 and 5 and 6, and in the tutorials later this week, so I do 3 tutorials per week, I can get to some of the more advanced questions later. All right, so let's get into it. So question 4, find the area of the region bounded by these two curves. Now, this is a classic problem that you might have seen at high school in your calculus classes there. The way I'm going to do this is to firstly show you a picture using GeoGebra. Did someone say GeoGebra? And then I'll do it more with sort of pen and paper. Okay, so we've got two curves, y equals x and y equals x squared minus 2. What is the area of the region between those two curves? Okay, so did someone say GeoGebra? Let's go and have a look. Here's one I've prepared earlier. Okay, so if I blow that up, you can see I've put in the line y equals x, and I've put in the parabola x squared plus 2. And you can see that, well, it looks like they cross at x equals -1 and x equals 2. So the region that you want is in here, the area of that region. Okay, and yeah, GeoGebra can do integration. So if I define h to be the integral, the integral between these two functions, between x and x squared minus 2, from x equals -1 to x equals 2, then yeah, it gives you an answer. Okay, it gives you an answer. So we get 4.5. So we kind of have some way of understanding this visually by GeoGebra. What's really important here are the limits of integration. So we need to work out, you know, where the two curves cross and which curve is above which curve. Okay, so let's do this by hand, and we can have a go with my document camera. All right, so this is question 4. All right, so we want the area so let's say we label these as our two functions. What we would like to do is find out where do those functions intersect, or the graphs of the functions, where do they intersect? Okay, so our curves intersect when x equals x squared minus 2. So here we've basically got a quadratic equation, and we want to solve that for x. Right, and we can factor the left-hand side. So x, these are the x points where the two curves touch, just like we saw in the GeoGebra picture. All right, and we also saw that on this region, x is above x squared minus 2. Okay. So f is greater than g on this interval. Okay, so now let's apply our calculus, our integral calculus, to compute the area. So the area between our curves, let's call it A. It's going to be the following. Okay, little a here is going to be -1, b is going to be 2, f is this, g is this, and so let's work that out. Okay, so it's pretty easy to integrate this. We can integrate here. So I'm going to get 2x. And this is from x equals -1 to x equals 2. So if you put those numbers in, I guess I can do that. So you put the first one in and you put the second one in and you take them away. Okay, I'm sure you've seen all of this before. Okay, then you simplify that and you'll get 4.5. Okay, now if you wanted to go a step further, you could put, square units or u squared just to make sure that you're clearly marking that it is area that you are looking at. Okay, so a couple of strategic steps there. The first thing that I like to do is draw a picture. Okay, and I use GeoGebra for that. The second thing is you want to work out where the curves intersect and which curve is on top. Okay, then you can use this integral formula to help you out, and you just compute the integral. Okay. All right. Let's have a look at another one. Let's go back to the PDF, and we can have a look at another question. All right, so I thought we could have a look at question 5. So there's 2 questions here. Part A is just, you sort of just grind it out. Let's have a look at part B first, though. Okay, I'll do part B first, and then I'll do part A first. Can anyone in the chat think of a really fast way of doing 5 part B? What might be a very fast way of doing it? Anyone know? 5 part B. Van Andrew. Triangles. Yeah, I like the way you're thinking there, buddy. So one way to do 5 part B is to draw a picture and just to look at the area, and you're going to get the area of triangles. So let's do that quickly, and then we can move back to part A. All right, so let me go back here. All right, Rahul, what do you mean? Oh, you mean split it up into two functions, right, Rahul? Is that what you're thinking? Yeah, you can do that. You can definitely do that. Okay, so let's consider, let's call it I, and it's this function here, isn't it? Now, let's think about Van Andrew's suggestion first, and then we'll move to Rahul's suggestion. Okay, so what does the absolute value function look like? Well, it's going to be something like that. Yeah. So it's a very famous function in mathematics, this absolute value function. And what are we actually looking to calculate here? Well, we know that if the graph lies above the x-axis, then the integral between, say, -4 and 2 gives us the area between the x-axis and the curve or the graph. All right, so as Van Andrew was saying, these are just two triangles here, right? So that one's going to have a height of 4, that one's going to have a height of 2. So let's call this A1 and A2, where A1 is the area of the first triangle, A2 is the area of the second triangle. So this will be a half of 16, so 8, and this will be a half of 4. Okay, so I like that way of doing it because it just uses a picture. But let's have a look at Rahul's suggestion now. Okay, so alternatively, right, we can think of this as two areas. Remember, x is defined in the following way. The absolute value of x. Right. So let's break this up into two integrals. So when x is negative, so on that interval there, our function is just negative x. Right? And you want to add in the other one. So when x is positive between 0 and 2, our absolute value is just the regular x function. Okay? So now we can compute those separately. And then we can simplify our answer. Okay, so the zeros are not going to contribute to anything. You're going to get 8 plus 2, which is 10. Okay, so what do you think? So on the chat, let me know, do you prefer solution 1 or solution 2? Which one seems more like better to you? Let me know on the chat. Do you like this way of thinking, the first solution or the second solution? Let me know. Julie is on to solution 1. I like solution 1 too. So is Oliver. Yeah, Ben too. It's hard to beat this one, but this is interesting too, right? If you can draw a picture, then this seems reasonable, but this is a bit more work. All right, thanks for chiming in, everyone. So let's have a look at part A then. You know, a few years ago, I taught a student, and whenever I would say, look at part A, he would always say, part A, let's party, everybody. Sorry, that's the maths joke for this morning. Okay, so I'll just put that in the chat so everybody understands that. Okay, so part A, 5 part A. Okay, so this is not a difficult problem, but let's just go through it anyway. Grab my notes. Yeah. All right. So we've got this function here. It looks quite difficult, but note that we're integrating between x equals 4 and x equals 9. So we can actually divide the denominator into both terms in the numerator to simplify our integrand. When I say integrand, that's the function that we're integrating. Okay, so it's not a particularly pretty function, so let's try to simplify it. Okay, so go back to my document camera. Okay, so all right, part A. All right, I think Rahul's already solving this in the chat, which is great. So we'll divide this into this one, this into this. Get the following. So you're going to be left with that. And it'll be minus. Okay, so we're integrating two power type functions here. So you increase the power by 1 and you divide by the new power. That's essentially one of the rules for integration. So x to the 3 on 2, you increase the power by 1, you divide by the new power, which is the same as just multiplying by the inverse. So x to the negative 1/2 will become x to the 1/2. Dividing by 1/2 is the same as multiplying by 2. Okay, when you put in these numbers, you're going to get, I won't do it all, but you're going to get something like this. So you've got the square root of 9 there. Okay, so you're going to get some square roots there, and when you simplify this, you will, I won't put all the details down, I think you get 82 2/3. All right, there's a question in the chat. Cameron, Julia, good question. So, let me make sure I've got the, oh yeah, so there we go, I've messed up the sign. So when you differentiate that, you don't get that, do you? So let me fix that up. Thanks, folks. Okay, so that's a good way of checking. When you differentiate this, for example, you want to get that term. And so you can see I put a plus in when it should have been a minus. Okay, thanks, folks. Okay. Let me move over to a slightly more challenging problem, even though I got my sign wrong on that one. By the way, can anybody remember who did this tutorial last week? Can anyone remember? Because I was sick. I'm just curious to know if anybody can remember who the tutor was from last week, week 9. Let me know in the chat if you can remember who it was. All right. So let's have a look at this question here. Okay. Chris Rockwell. I hope you had a good time with Chris. All right. Find a function. So we're asked to find a function that satisfies the following integral equation. So this is a special kind of equation called an integral equation. It has an unknown function, f, inside it. And in this context, you want to find the function f that satisfies this equation. Now, I think what this question is designed to do is to get you applying the first fundamental theorem of calculus. Okay, I think that's what this question is designed to do. Okay, so the first fundamental theorem of calculus basically says that if you differentiate an integral, then there's a form that results, and basically, you know, differentiation pretty much undoes integration. All right, so let's have a look. I'll just make some notes now on my document. Okay, so this is question 6. So we want to solve the following equation for f. Okay, so let's just slow down for a second and consider this problem. The first thing you'll see is that you've got these t's here and x's in the integral sign. So you can interpret that as, well, t is sort of a dummy variable. It doesn't change the left-hand side. And the x means that if you knew f and you could integrate, then this whole left-hand side would be a function of x, and the same on the right-hand side. Okay. So how can we use calculus to sort this out? I kind of hinted at it before. So let's call this star. And what I'm going to do, I'm going to differentiate both sides of star. And what that does is it gets the f out in the open. So the strategy then, let's differentiate both sides. The integral signs are going to disappear, hopefully, and then we can sort of solve for f. Yeah. So the plus x, yeah, the plus x, that's a good question, Rahul. I've just put it on a different line. This is the whole of the start equation. Okay. So you're not integrating this because you've already got your dt there, your differential there. So this is separate. So this right-hand side is a function of x. This left-hand side is a function of x. Okay, does that make sense, Rahul? Okay, good. So we're just leaving that alone at the moment. All right. So when we differentiate an integral sign, we know that, okay, if let's say the left-hand side is this, right? What will this be? Yeah, Julia, yeah, we definitely, because this is a function of x up here, the whole thing is a function of x. You can change the t, and you're not actually going to change anything really here. It's the final integral variable. That's the important one. Okay. All right. So the left-hand side is this. Who can tell me in the chat what will this reduce to by the first fundamental theorem of calculus? Who can tell me? Yes, Julia, on the case. Okay, so that's the left-hand side. What about the right-hand side? Well, it's not quite in this form. Let's change it so we can put it into our special form. Okay, yep. So I'm going to take your suggestion, Rahul, and switch the order of integration. Okay, so now let's differentiate both sides. So this is going to be negative x squared plus f of x plus 1. That's by the fundamental theorem of calculus, the first fundamental theorem. Okay, so now what we want to do is that's your right-hand side differentiated, that's your left-hand side differentiated. So you want to bring those two things together and solve for f. So let's make f of x the subject. You can bring the f of x over there and then factorize. So I'll bring that over to the other side. And now just divide the whole thing. That's it. Okay. So even though that was a H problem, I mean, differentiating this integral is easy by the first fundamental theorem of calculus. You just remove these things and replace t with x. Here it was a little bit more difficult because this form is a little bit different to this form, but we could put it in that form. Okay. So there it is. So this is the function that satisfies the starred integral equation. Okay, now a lot of the times you'll be looking at differential or integral equations and it's actually impossible to solve them explicitly, but in this case we could do that. Okay, so once you know how to do it, it's not too bad. Okay, let's have a look at another integral equation. I'm looking at question 9 here. So this is another H1, but let's have a look on the PDF. Okay, let me make that a bit bigger. Oh, too big. Oh yeah, no, that's okay. All right, so I'm looking at question 9 here. So question 9 also kind of has an integral equation. It's got an equal sign and it's got an integral sign. So it's kind of known as an integral equation. All right, so let's read it carefully. Suppose that capital U is a function whose derivative equals this little u. We don't know what capital U and little u are. Okay, first part, find the derivative of big V if big V is defined this way for some constant A. All right, let's do that first before we move on to B. B is sort of some relationship between big U and little u involving integrals. But let's look at part A first. Okay, so all right, so let me go back to my document camera. Yeah. All right, so we know that there is the following relationship between, let me write that a little bit differently. U So that's what I'll do to denote capital U. That's what I'll use to denote lowercase u. And I'll do V a little bit differently. Okay. So I'll make that a bit sharper than that one. Oh, that's X. That's not a dash. That's just big U of X. Okay, so that's a U. That's a V. Okay. If A is a constant, and this is how we define our capital V, what is the derivative of capital V? So we've got two things to differentiate here. We're differentiating with respect to X on both sides. Okay, so this is a product. So we would expect to differentiate that via the product rule. And for this one, we'll use the FTC, the first fundamental theorem of calculus. Okay, so let's do that. If we differentiate this, we'll get negative dash of X, so product rule, and if you have that, get that. So that's the first part taken care of. And then the fundamental theorem of calculus says, well, I cover up the integral sign and I replace t with x, or whatever the dummy variable is. Okay. There's a couple of things in the chat. Hang on, a couple of questions for the first one. Oh, yeah, no wonder yeah. Thanks, folks. So that's just U. Okay, so I put U dash there, I shouldn't have done that. Okay, thanks for the reminders. All right, so this is going to cancel off with this because that's negative big U, that's positive big U. When we get down to this, what is the derivative? Well, it's defined as little u. So we can write that as this. Okay. All right, thanks for your corrections. Okay, so that's the first part of the problem. The second part asks you to do the following. All right, part B, hence, so you use something from part A to show that the integral of capital U from 0 to A is this mess here. Okay, so let's have a look at how we can do that from part A. So I think what we're going to do is do some integration. So let's see if we can do that. All right, so from part B. All right, so what do we have from part A? Well, if I integrate both sides of this final expression from part A, what am I going to get? Well, I can use the fundamental theorem of calculus to help me out here. All right, on the chat, who can tell me what will this right-hand side simplify down to? If you were doing this, we can't really simplify this much. Yep, you're on the right track there, Osmond. Don't forget the v of 0 here as well. So if we integrate derivative, it's going to be v of a minus v of 0. Okay, so now what? Well, we haven't touched this left-hand side. So what is u, little u? Little u is just the derivative of big U, right? So you can write it like this. This is the left-hand side. Yeah. Yeah, and then you can integrate by parts. Okay, what is, just let me check something here. What is big V of A? Big V of A will be, well, that'll be 0. And that'll be that. Oh, okay, I don't think I actually need to simplify that, right? So hang on, let me just, yeah, I don't actually need to simplify that. Let me just adjust that, because I can look back here and I can go, okay, V of A is going to be, so replace X with A here. That's U. And what is V of 0? Well, X is going to be 0 here, so A minus 0 times U of 0, big U of 0. And this second thing is going to be 0. Okay, so now what I can do is rearrange this, make this the subject, okay, so I'm going to take that to the other side and make this the subject here. Plus, yep, oh, plus. Here we go. And I think that's what we wanted, wasn't it? Da, da, da. Yep. So let me just go back to the PDF and we'll just see if we can. Okay. Now we wanted to show that this equals that. Now we've got t's instead of x's there. It does not matter. Why? Because x is the dummy variable here. Okay, so let me go back to my thing. Document camera. So, okay, so even though I've got t's here, I could have x's as well, it doesn't matter, okay? So even though I've got t's here, x's are still, you can just replace them with x's. So you get the actual thing that you need. Okay, so you can see I tried to go down a different path there, but actually we didn't need it. We didn't need it. So I think the first part's pretty easier. The second part's maybe a little bit harder. All right. Okay, let me move this on a bit. Okay, just give me a sec. I'm just looking through my notes. Just bear with me. All right, let's have a look at 13. Okay, so these kind of problems, you're basically differentiating integrals in all of these ones. Okay, so let's do a problem, and we keep in mind that the first fundamental theorem of calculus basically says that you can differentiate an integral, and the derivative undoes the integral. Okay, that's pretty much what it is. So let's have a look. Let's have a look. So in 13, you've got the dummy variable is t, so you can swap that out, who cares what it is, and x is the independent variable, right? So this whole thing is here is a function of x. So what do we do when we differentiate it? Okay. So let's go to my document camera, and we can have a look. All right. So consider the derivative of this function here. All right. Now, the fundamental theorem of calculus pretty much says that if you are differentiating an integral like this, then the differentiation and the integration, they cancel out. Okay? Now, so basically that disappears, and the t gets replaced with x. Now, there are some assumptions, of course, around the fundamental theorem of calculus, but from an operational point of view, this is kind of what you're doing. Okay? Now, one of the problems here is that this doesn't match this format. So can anyone suggest in the chat how we might make this format, yeah, change this one? So Osmond's on the case. So what we can do is, yeah, flip the order of integration. Okay, and now that negative sign can come out there, and we can do the differentiation as we expected, right? So now what we can do is apply the first fundamental theorem of calculus. Ah, Dharam, good question. Am I missing a term there? Am I missing a term? Have a think about it. I don't think I am. So this disappears, and x goes in here. Okay, so I'm not missing a term here. Dharam, you're thinking of the second fundamental theorem of calculus, right? You're thinking of something like this. Okay, that's A. Dharam, you're taking that. This is what I think you're thinking of. Okay. Yeah, Zia. So Zia's got a great question on the chat. Can I confirm that t is just a randomly assigned variable? Yeah, I call it a dummy variable. It doesn't make a difference. The only thing that you wouldn't want here is x. You wouldn't want to replace t with x here. Okay, you can let it be whatever you want. Okay, elephant, puppy, whatever. Okay. So Dharam, can you see what I've got there? I think this is like the first one is number 1, and this is sort of number 2. Okay. So Dharam, there's no f of a in this one, but there is an f of a in this one. Are you with me? Well, the f of a had okay, this is just a constant, yeah? Imagine you integrated this from here to here, and then you differentiated the answer, right? This 4 will give you some constant in your answer. But when you differentiate it, as Osman's already said, it disappears. Okay? So it's a really good question, right? So that's the reason why there's no 4 or anything in here, because when you differentiate it, you get nothing. Yeah, exactly, Dharam, because the constant is arbitrary. I think Osman was hinting at that before in the chat. Okay. All right. So a couple of things. Look, Dharam, people get confused because there's two fundamental theorems of calculus. And it's like, well, which one do you want? Which one do you want? Oh, party. Sorry, I didn't get that there. All right, folks. Look, it's been nice knowing you. And I know we've been apart, but hopefully one day I can meet you, or you can come to Sydney and meet me. But look, I've had a great time this term, and I know it's very hard. Everyone's sort of isolated or in different parts of the world. But yeah, I really enjoyed getting up on a Monday morning to chat with you. And yeah, who's doing 1, 2, 3, 1? Math 1B. Anyone? Okay, so my best advice for Math 1B, you can do it, right? The algebra is more challenging than the calculus. So in 1131, many students tell me the calculus is hard, but the algebra is easier. Okay, in Math 1B, it's usually the opposite. People find the algebra a bit more difficult, and the calculus is a bit easier. Okay, well, good luck with that, Julia. It's up to you. If you get a high distinction in 1131, then probably 1241 is a good choice. But you can always move, right? You can always move between classes if you want. You could try 1241 and then move to 1231 if you wanted. It's up to you. Yeah, again, 1241 is more about proofs and going sort of a bit deeper in and some more stuff. But look, yeah, part A. So enjoy the day, enjoy the week. Good luck with your exam. I want everyone to get the mark they want, whether it's a high distinction or distinction, credit, pass, whatever. I hope you get the mark that you want. And hopefully I'll see you again. All right, so I will sign off and bye and good luck. Nice knowing you all. So do come and say hi. Feel free to email me and enjoy the day.